Hello and welcome back to Dr. Logic Awkwardly Does Logic. Today, we are going to begin proving the completeness of S5. That is, if we have a class of frames that is reflexive, symmetric, and transitive, then any formula that is valid on every single frame in that class will be provable in S5. So here we go. We've got two lemmas that we're going to do. So it's essentially a two-step process. One of these lemmas says that if something is valid on this class of frames, then it passes the test. The other lemma says, if it passes the test, then you can prove it. Not only that, I'm going to show you how to prove it. So you can see now where this test and all the work that we did to get up to it, why it's so important, because it's the linking thing between being valid on the class of reflexive, transitive, and symmetric frames and being able to give a constructive procedure that generates a proof for it. So we're going to start today with just the first of those two lemmas. So let's get up here. What we are going to prove overall is that, so let C be the class of reflexive, transitive, and symmetric frames. Then if phi is valid on that class of frames, then in S5, we can prove it. So that is our main goal. As I said, we're going to have two lemmas that get us there. The first one, the one we'll prove in this video, is let C be that class of frames. We're going to show that if phi is valid on the class of frames, then phi in ordered modal conjunctive normal form passes the test. So this is step one of the proof of the entire theorem. So the way that we're going to prove this is we're going to prove it contrapositively. Proof contrapositively, that is, if phi in ordered modal conjunctive normal form doesn't pass the test, then we can construct a countermodel, on a reflexive, symmetric, transitive frame where phi is false. And this is again going to be a constructive procedure in the sense that once you have a formula that fails to pass the test, you can read off of that failure what the counter model is going to look like. So you will always be able to actually generate the counter model that you need. So this is what we're going to try to show. Now, let's note something important. If phi doesn't pass the test, then some conjunct of it fails to pass the test. Now, if there's more than one, it doesn't matter. We just need to find the one. So this conjunct, this one that fails to pass the test, is of the form beta or necessarily gamma 1 or up to necessarily gamma n for some possibly 0n or possibly delta. So our purely propositional bit, our various necessity bits, and our single purely possible bit. And so this is what we know from the fact that this conjunct doesn't pass the test. We know that it has this form, and none of beta or delta, gamma 1 or delta, all the way up to gamma n or delta is a tautology. So here again, we are just reading off what it means for this conjunct to fail to pass the test. So none of these is a tautology, And all of them are purely propositional because remember, we've stripped off all of the modal operators. So let F be a reflexive, symmetric, and transitive frame with at least n+1 worlds. So the n here is the number of gammas that we have. So we need to have at least one more world than we have possibility formulas. So let's label each of these W0 all the way up to Wn. We define a model on this frame F as follows. We let the value of beta, which is purely propositional and not a tautology, so it can be falsified, whatever we need it to, the value of beta at W0 is going to be false. And we know we can do this because it's not a tautology and it's purely propositional. So that is the first part of our model. Whatever we need to make this formula false, we do that at W0. We then let the value of gamma I at world I be false in exactly the same way. Each of these gammas is purely propositional, not a tautology. So you can just falsify it at that one world, define your valuation however you need to in order to make gamma I false at Wi. And this is why we needed to have possibly one more world than we had gammas, because W0 is the world that the purely propositional part of the original contract was. So this gets us that all of these betas are false, all of these gammas are false, and at least one world in this. That means beta is going to be false, and also because every world can see each one of these gammas, none of these necessity claims are going to be true at W0. So we also know then that because beta or delta is also not a tautology, we let the value of delta at W0 also be false. So this gets this disjunction false at the actual world. In fact, what we can do is ensure that this delta is false at every world. So that will then mean that this entire disjunct will be false at W0. This one will be false at W1. This one will be false at Wn. And because that is as many worlds as we have, so here, let me go back and try to both write and say at the same time. It's way more complicated than you think it might be. So also let the value of delta at every other Wi be false. So then we have that at W0, necessarily delta is false, because every world that W0 can see, delta is false at it. So that is how we ensure that each one of these disjunctions is itself false. So the value of beta at W0 equals false. For every gamma I, there is a Wi such that W sees Wi. Remember, reflexive, symmetric, and transitive, they can all see each other. And the value of gamma I at Wi is false. So as I just said, necessarily gamma I is false at W for each gamma I. Ooh, let me see. I don't want to go to a new page, so I'm going to erase the statement of the lemma. Just remember that what we're trying to prove is that if phi doesn't pass the test, then we can create this counter model. So we've gotten part of the way there, and we don't have too much further to go. So no world, as we said, makes delta true. So possibly delta is false at the initial world. And this is what we need, because now we have that beta is false at W0. Delta is false everywhere. So possibly delta is false at W0, and each of the gamma I is false at W0. This means that our conjunct, because it's of this form, every single one of these disjunctions is false. Therefore, the conjunct itself is false. Therefore, the entire conjunction that it is in is false. Therefore, you have shown that this formula, which doesn't pass the test, is not going to be valid on the class of reflexive, symmetric, and transitive frames. I feel like this was very wordy and not quite as perspicuous as it might have been. So I am going to go, let's get a new whiteboard. Let's just kind of see this a little bit diagrammatically. So we've got our conjunct. It looks like this. Oops, sorry, that should be a gamma n, gamma 1 to gamma n, or possibly delta. So our frame looks like this. We've got W1, W2, W0, W3. Let's suppose, just for the sake of making it easier, that we've got we've got 3 of these. So then we make beta false here, gamma 1 false here, gamma 2 false here, gamma 3 false here, and we make delta false, delta false, delta false, delta false. Now, because this is a reflexive, transitive, and symmetric frame, where we've got all of these, one more relation in there. So every world sees every other world. This is reflexive, transitive, and symmetric. So now we have that necessarily gamma 1 is false because W0 can see W1. Necessarily gamma 2 is false. Necessarily gamma 3 is false because it can see each of these. Delta is false at all of these, so possibly delta is false. That means we've got this disjunct is false, this disjunct is false. All of these other ones are also false. Possibly delta is false. So the entire conjunct is false, and that means that the whole conjunction this conjunct is in is false. And the trick to remember, the reason why this always works, is because each one of these formulas is purely propositional and not a tautology. So you can always come up with a valuation that makes it false at an individual world. So hopefully this picture is a little bit more perspicuous than the slightly wordy and messy proof on the other slide. However, it's showing you the same thing. So that is step 1. We go from validity on the class of frames to passing the test. And we put this contrapositively. If it doesn't pass the test, then it's not valid on the frame. In the next one, we'll do the second step, which says that if it does pass the test, then we can give a proof of it. So join me next time where we get to do more cool things with the completeness of S5. Until then, take care.